So this is case 3 of trigonometric substitution. So if we have a difference of u squared and a squared, so we let u be equal to a times secant of theta. So case 1 was a squared minus u squared. Okay, so the u is on the hypotenuse side because it's the one in the minuend, and the one with the constant is in the subtrahend. Okay, so we put, okay, again, the u on the hypotenuse of the right triangle. Okay, and the constant is either on the opposite side or the adjacent side. So if we're going to put it on the opposite side, so we'll be using hypotenuse and opposite side. Okay, and it would be um we'll be using hypotenuse over opposite because the variable must be on the numerator. No, so we'll be dealing with cosecant. The reciprocal of sine, no, is cosecant. If we're going to put the a at the adjacent side of the right triangle, then we'll be using secant. So it would be better if we'll use secant instead of cosecant. So we'll have the constant a be on the adjacent side. Again, this is the adjacent side of the right triangle, and this is the hypotenuse. Okay, so if we're going to derive this, u is equal to a times secant theta. So we are going to get the ratio of the hypotenuse and the adjacent side. Okay, so that would be equal to the second trigo function. Okay, hypotenuse is u and adjacent side is a. So we now have u is equal to a times secant theta. All right, so if ever you forget this trigonometric substitution, okay, equation, then you can always go back to the right triangle, okay, get the relationships of the sides, and then form the u squared minus a squared. Okay, and then you'll arrive not to this equation. So do not just memorize, okay, the formula. So you need to understand it. Know why is it second and not the other trigo functions. All right. So for example, we have um 4y squared minus 9, quantity raised to the power 3 halves, and then all over y cubed dy. Okay, so it's a difference of a function of x being squared, a function of y rather being squared, and a constant being squared. So this follows no the case number 3 format u squared minus a squared. So where u no is 2y. Okay. So again, it follows the u squared minus a squared. So the u here is square root of 4y squared. It's 2y. And a is square root of 9 over 3. Okay. So again, if ever you cannot recall this equation, then you derive no that equation. Okay, so meaning if we're going to use this directly, so we would be using 2y. Okay, 2y is equal to 3 times secant theta, right? Okay. Or again, do not just memorize, no? So you need to understand why it uses secant and not the other trigo functions. So supposing this is the angle theta, okay? So we need a ratio of u and a to form no, a trigo function. So since the u is here at the minuend, okay, before the subtraction sign, okay, so meaning it's the square of the hypotenuse, no, 4y squared is the square of the hypotenuse. So meaning, okay, 2y is the hypotenuse, no, square root of 4y squared is the hypotenuse, and the adjacent side, again, we use adjacent side instead of the opposite side so that we won't be dealing with cosecant. It would be better if we use secant. because it's simpler, no? If compared to cosecant. So A therefore is on this side, no, the adjacent side of the right triangle. So again, hypotenuse over adjacent side, no, is secant theta. So we are getting this ratio because we need to put the variable on top of the fraction and the constant here. Okay. So that's why we are writing it as hypotenuse over adjacent and not adjacent over hypotenuse. Although we can also do that, but we are going to arrange pa na the expression so that we'll end up with a y, okay, on the left side of the equation. Can always write it as adjacent over the hypotenuse and use the trigonometric identities. No, this is cosine, right? So if we're going to follow that, adjacent side is 3 and it's 2y here. So cosine theta. So if we're going to solve for 2y, it's 3 over cosine theta. So meaning 3 times 1 over cosine theta or 3 times the reciprocal of cosine theta, which is secant, okay, theta, right? So we end up with the same equation, no? So 2y is equal to 3 times secant theta. All right. So solving for y because we need to substitute, okay, something to the y cube here. So divide the equation by 2. So we get 3 halves secant theta. So let this be our equation 1. Okay, then solving for dy for equation 2. So derivative of secant is secant tangent, right? So let this be equation number 2. And for the third equation, we need to substitute 4y squared minus 9 raised to 3 halves with a function, a trigonometric function. So this can be written as square root of 4y squared minus 9. No? Square root of 4y squared minus 9. And then quantity raised to the power of 3. Okay, all over y cubed dy. So from this triangle, okay, this opposite side is square root of the square of the hypotenuse, so meaning 4y squared, minus the square of the adjacent side, meaning minus 9. So always pair this with a constant if we are going to write an equation containing this, because it would be easier to use that compared to dividing it by 2y because you'll be dealing na pod with a variable, no? So it would be better to deal with constants instead of variables. So, square root of 4y squared minus 9, we divide it by the constant. So that's opposite side, no, over the adjacent side. So meaning OA or tangent theta. So square root of 4y squared minus 9, therefore, is equal to 3 tangent theta. So let this be our third equation. So we'll use these equations to transform this into trigonometric, no, integrand. So square root of 4y squared minus 9 from equation 3 is 3 tangent theta. So you need to raise this to a power of 3. And for the y cube, it's 3 halves secant theta. Quantity raised to the power of 3. Okay, and the dy. So before writing the dy, okay, as you can see, no, it's this over y, and you can write it as one fraction and then raise the entire fraction to the power of 3, right? And actually, no, you can um transform it into opposite side over hypotenuse, which would result to a sine, okay? But We can do that, no? As long as we know our trigonometric identities. Okay. So it's ano, the exposure no, to the different examples. Okay. So I'll show that other solution, no, pero it will be dealing with sine and not with secant and tangent. Okay. So let's just continue. So dy from equation number 2 no, is 3 halves times secant theta tangent theta. So that's 3 halves secant theta okay, tangent theta d theta. So simplifying, we have 27, no, 3 cube is 27, tangent cube theta, and then all over 27 over 8, second cube theta, and then 3 halves, no, second theta, tangent theta. So this supposedly will form the du if we have only second in this fraction, but since we have tangent, okay, so we transform it into second, okay, but we can easily transform it to second if the power here is an even number using one of the Pythagorean identities, but since it's odd, so let's combine first the two tangents here so that we can see what we can do with the tangent and the second. So 27 over 27, that can be canceled out. So 8, okay, this can be written as 8 over 1, no? So times 3 halves, so that's 24 over 2, or that's 12. Okay, and then tangent, we have 3 and 1. 3 and 1 here. So it's raised to the power of 4. And while second, we have 3 at the bottom and 1 here. So meaning only 1, okay, or only 2, no, seconds at the denominator, d theta. So second squared is at the bottom. Huh? So if we put it at the top, it becomes cosine squared. No, the reciprocal of second is cosine, or it becomes second raised from -2. Okay, but tangent can be written as a function no, in terms of second squared. Okay, by raising no tangent raised from 2 to a power of 2 to get tangent raised from 4. So we can relate it to the second at the bottom. Okay. So we do not use solvable groups yet because we can divide pa man, no? If we transform the numerator to second, then we can divide it by the second squared here. And we'll see later if we'll use or we'll need no, the different solvable groups of trigonometric integrals. Okay, so this can be written as second squared theta minus 1. This is equal to tangent squared, no, using one of the Pythagorean identities. And then you square it so that it will be equal to tangent raised to 4. Again, this is using one of the Pythagorean identities. No, this is equal to tangent squared. And then divided by second squared theta, d theta. So we can expand the binomial. It's equal to second raised to 4 theta minus 2 times second squared theta times 1. Okay, and then plus 1 squared, or 1, and then all over second squared theta. And of course, the d theta. So we can divide each term in the numerator by second squared theta because the one in the denominator is just a monomial, no? So we can divide each okay, by second squared theta. So let me separate the terms na ahead. Okay, so this is 2 second squared theta over second squared theta, or that's equal to 2 times 1 na lang. Okay, 1 d theta or d theta. Again, dividing second squared by second squared, no, for the second term. And then for the third term, we have 1 over second squared. Okay, so we have plus the integral of 1 over second squared theta. Because we need to use different formulas, okay, methods in integrating, no, each term. So for second raised to the power of 4 divided by second squared. So this must be second squared na and not second raised to the power of 4. So we have a formula for this, no? Integral of second squared is tangent squared, or tangent rather, only 1 for its power. And minus 2 times integral of d theta is theta. Then plus, okay, 1 over second squared theta is equal to cosine squared theta, right? And we have the reducing power identity, or power reducing identity for cosine squared is equal to 1/2 plus 1/2, no, cosine 2 times the angle, so meaning cosine 2 theta. And you can integrate each term. Okay, integral of 1/2 is 1/2 theta, and integral of 1/2 cosine 2 theta is 1/2 times the neutralizing factor needed for the derivative of 2 theta. That's 1/2. So 1/2 times 1/2, that's 1/4. No? Then integral of cosine is sine. But take note, it's 2 theta. K plus C. Simplify before restoring the original variable. So this is tangent theta. Okay, these are similar terms to negative 2 plus 1/2. That's negative 3/2 theta. Then plus 1/4. Okay, and then we can use the double angle identity to go back to the single angle theta. So sine 2 theta, okay, is 2 sine theta cosine theta, okay, plus C. So before plugging in those expressions containing the original variables, let's simplify first. This is 1/4 times 2, or that's 1/2. Okay, sine theta cosine theta. Okay, plus C. Then we return the original variable, tangent theta. Okay, so we don't have a tangent theta here yet. Okay, so there's a tangent theta from equation 3. So it's square root of 4y squared minus 9 all over 3. Okay, and then for the theta, okay, we can actually use to any triangle function, but since we have written this first equation, okay, these are the bases for the dy, no? So we can use this equation, okay, to solve for theta. Bale, theta, okay, is from second theta. So from here, so let me label it as A. So from A, okay, so theta, no, is arc second of 2y, okay, over 3. So we'll use that for the theta here. So arc second of 2y over 3, and then plus 1/2 times sine theta is opposite over hypotenuse. Okay, so that's right. Sine theta. Opposite side is square root of 4y squared minus 9. And then hypotenuse is 2y. All over 2y, while cosine theta is basically the reciprocal of second. So cosine theta is 3 over 2y, or adjacent side over hypotenuse. So 3 over 2y. So cosine theta is 3 over 2y. So 3 over 2y. A plus c. So simplify. So this is square root of 4y squared minus 9 all over 3 minus 3 halves arc second of 2y over 3. Yeah, we have plus 1/2 times 3. 1 times 3. So that's 3 over, we have 2 times 2y times another 2y in the denominator. So that's 8y squared. A square root of 4y squared minus 9. A plus c. Okay, if you want to combine the 4y squared minus 9 here, okay, so you can also do that. Or if you multiply 12 to each of the terms here, so you can also do that. So 12, bale, no, times this is, it's 4. Okay. Square root of 4y squared minus 9, and etc. Or you can just have it written, no? This way you're factoring out, not 12, because it's a common factor. So you can have, this is the final answer, no? So this is the integral of 4y squared minus 9 quantity raised to the power of 3 halves all over y cubed, okay, dy. So this is for case number 3 of trigonometric substitution.